So good evening, everyone. My name is Christopher Lillian Stolpe. I'm the CTO for Solutions and one of the co-founders at Tigera. And since tonight's theme is about visibility, I thought I'd kick off the evening talking about visibility into communication paths and who's actually exercising communication paths in your infrastructure. So, title is Who's Really Talking? What are the real communication paths in your stack, both the ones you know and the ones you don't and didn't intend to have. So we're going to spend a little time talking about that, and after we're done with that, we're going to hear from Lightstep on application visibility, and I think that's going to be a pretty cool talk as well. And if there are questions afterwards, we're going to do a fireside chat if there are interesting questions. So, starting off, information exchange. Bonus points if anyone can tell me what that site is. But do you really know what information exchange paths exist in your stacks? If not you, who does? And are you sure that your information is correct? And if you're sort of wondering about this statement, it's like, what are you worried? What's there to be worried about? So let's talk a little bit about why you might want visibility into what's going on in your infrastructure, and also, why are we talking about this now? This isn't a new problem. So why are we talking about this now? And one of the reasons we're talking about this now is it's an existing old problem, but it's got some new contours. And that's because we're in this new microservice containerized world. And so I thought I'd call out some of the differences that you might see between getting visibility into your network in the heritage world, because legacy has such bad connotations, so we'll call it heritage world, and in your new microservice world. In the heritage world, a lot of your communications were opaque, or at least much more difficult to surface, because most of them happened within the bounds of a compiled application. So they were making library calls, etc. It was inter-process communication, maybe, but it was very much opaque to within the bounds of the application. So surfacing what was being communicated was somewhat more difficult. Also, applications were big and complex with lots of connectivity requirements that have grown over potentially decades. So actually knowing everything that a given application or compiled binary needs becomes a bit of an interesting exercise. For those of you, I'm sure no one has ever had this experience of firewall cruft. It's like no one ever touches the firewall rules because you never know what you're going to break. You don't think that rule's being used anymore, but do you really know? A good little story on that. Not quite firewall rules, but it's an interesting case in point. A large company I used to work for, who shall remain nameless, I will protect the guilty, had a mini, as in a Sperry Univac mini, still sitting on the machine room floor. The screen, the VT220 equivalent screen, for those of you who are old enough to remember VT220s, was pretty much almost completely dead. You sort of had to look at it just the right way and shield it so you could actually still see the text. And so people say, this thing hasn't been touched in literally years. It must not be necessary. So they turned it off in a maintenance window. And sure enough, the next day, no one was screaming, so they let go for a couple weeks and said, okay, no one was using this anymore. And you know where the story is going, because they pretty much decommissioned it. It had been rolled out but not thrown in the dumpster yet, and all of a sudden, quarter end close fails because there was some component of the booking system that still evidently had some little dependency on something in that Univac mini. So it became not only get the mini back up, but even to the point of trying to find anyone who knew how to recommission a Sperry Univac mini in end of 2009-ish time frame. So do you really know who's talking? And when was the last time anyone vetted that? However, the thing to keep in mind with the heritage environment is external connectivity was usually pretty understandable. It was a very specific requirement. This application needs to talk to this application. So for the connections that do exist, and you go to the trouble to figure out what they are, you sort of knew what they were doing. Let's step over to the microservice world. The green point on this one is microservices are simple and have lots less input-output chains. So really, if you think about a microservice, if you do this right, if you forklift your heritage application into a container and think that's going to solve all your problems, what you actually just did was bought the worst of both worlds, and you brought all the sins along with you. It's not going to get you out of trouble. So if you refactor and you go into a microservices infrastructure, each microservice does one thing. It does it. It's a fairly well-contained, well-understood little box, and has a limited number of input and output channels. So understanding each microservice's requirements should be somewhat easier. However, there are a lot more of them. And because you're no longer doing things as library calls, etc., everything was a library call before is now a HTTP REST call or a gRPC call or something along those lines. So there's a lot more of intra-microservice communications. Might be a few channels, but there's a lot more going on over those channels. And many of these are in the weeds API-specific things. Basically means it's going to be a little bit harder to understand why does this microservice need to talk to this microservice and what's it doing, because everything you used to build in is now externalized. Another advantage, which I didn't put out here, is because it's surfaced on the network, it makes it somewhat easier to take a look at. Other interesting environmental challenges in these models. Heritage is or was static, or mostly so. Most people think VMs, as a general rule, are dynamic compared to physical servers. They are, but most VMs still last months or years, and their identifiers are also somewhat static. And this becomes sort of interesting. We talk about network logging in a little bit. And an IP address for a given service will probably always be the IP address for that service over the lifetime of that service. So, and you measure these things in calendar time. VMs are measured as in what day or what month or what quarter you stood the thing up in. The flows are also somewhat static. Because these things are basically static, you're not pushing code quite so frequently, etc., that once you've characterized your network flows, in this kind of environment, they tend to be more static or stable than in the new world. In the new world, one of the reasons we're going to microservices is to get development velocity and feature velocity, which means we're pushing code more frequently. So endpoint lifetimes are measured in clock or even stopwatch time. So now your pods, your containers, are coming and going in order of days, hours, minutes, and sometimes even seconds if you're doing per call servicing, say, a serverless style config. Because endpoints are changing very frequently, the identifiers for those endpoints are also changing fairly frequently. If you think about this for a minute, you might have, let's say, take a Kubernetes environment, for example. IP addresses don't have any real meaning other than it's a way to get a packet delivered to a given thing at a given point in time. What does that mean is the IP addresses are reused by Kubernetes, and it's not bound to what the thing was. So that IP address that started off in the morning being your database server, by lunchtime could be a front-end application, and by evening could be a new shard of a Redis database. So that IP address is potentially going to identify different things at different points in time. If you start thinking about how you do network logging today, you should maybe start being really concerned about this. Because yeah, an IP address did something. Well, what was that IP address at that point in time? And flows are constantly changing. Developers push new features require new connectivity. So the flows that you recently learned and said these are good, 15 minutes later are no longer relevant. So this becomes an interesting race for, in fact, we were having a conversation earlier about machine learning. It becomes an interesting machine learning challenge because the pattern is constantly changing, A. B, because it's changing, it also becomes a little harder to figure out, are you learning a good pattern or a bad pattern? Right, so there's some interesting artifacts here. So who cares who's talking? How many people have seen this slide before? The people who care are here, and these are the folks who are chasing down this wonderful road, right? So somebody's got to clean up the mess that comes from the unicorn. So why do the people who have a security mindset, and it's not just security, I mean, we all pick on security, but it's a good idea if you're developing an application or you're an estate owner to actually know what's dependent on what. But let's take the security case. Why do security folks care? In a native Kubernetes environment or any other high-skill environment where you might have 100,000 pods currently running, you would have potentially 100,000 pods fully meshed with potential communication channels, of which only a small subset are actually being used. So you have this rich connectivity graph, any pod should be able to talk to is able to talk to any other pod. Only a few of those are useful. All the others are useful, but not just to you. So the communications that are happening, are they really ones that you want to have happen? This is the graph you would really want. So you know, if you can identify which of these flows should be happening, it makes it easier to log them. And also, you can isolate out such that the unauthorized flows don't get a chance to get into the environment. A good example of this is something called lateral movement. Most of the major hacks we've seen today is somebody getting something in somewhere in your infrastructure. There's no controls on that something, and that something then laterally moves around, sometimes over months, until it scouts out exactly what it's looking for. And if you're lucky, they tell you as they're exfiltrating the data, so at least you know you have been screwed. Very often they will not tell you, and you will find out that you were screwed at some point later on the front page of the New York Times or the Financial Times. So, or no one ever finds out. So lateral movement is a problem, and lateral movement is enabled by having basically A, free connectivity between any endpoints, and B, not being able to monitor that to at least know something suspicious is going on. So we're talking about visibility, but I'm going to talk a little bit about how you achieve this. So for example, Kubernetes network policy allows you to define a set of policies that define your communications graph. And I'm not going to spend a lot of time on this, but you can write a network policy that's very simple, that basically says things of type role ratings can talk to things type role DB, whatever that might be, so it's identified that way, but things like a role helper won't be able to talk to anything. This becomes interesting when we start talking about tracing and logging later. So you can write a policy that allows that statement to be enforced across the infrastructure, and we're supposed to talk about what that means, but it's basically a simple policy. The nice thing about these are simple policies. You can write policies that identify a type of a flow. You can write a database client to database server policy that will identify all flows between database clients, a specific database client to a specific database server, or LDAP clients to LDAP servers, or whatever it might be. You can write policies to identify and classify specific types of traffic in your infrastructure. So you can write these policies, they're composable. So let's say I have a policy that says foo clients can talk to foo services and bar clients can talk to bar services. And if I do this, then something that's a foo client and a bar client can talk to both foo and bar services, but something that's a foo client can only talk to foo client, foo services. And each of these gives us now a key to monitor the flows. So, as I said, we're supposed to be talking about visibility. Visibility and policy can be, especially at scale, should be two sides of the same coin. If you don't have some kind of way of identifying what the flows were and what allowed them, you will have a huge morass of data that you will try and make sense out of. Whereas if I can classify it up front, it gives me a better chance of actually detecting patterns and seeing things that should or should not be happening in the infrastructure. We often talk about visibility as being something from a security standpoint, a flow happened that shouldn't. It can also be a troubleshooting standpoint, though. Flows that should be happening aren't, right? So that's another use. So let's talk a little bit about flow logs and what you might get if you have policy-driven infrastructure. So first, let's point you at an existing flow log, and for those of you who use a certain cloud service, you'll recognize what this is. Remember I said earlier that IP addresses are ephemeral. If these are the kinds of logs I get, now I have to figure out at what was 192.168.94.163 at exactly 17:41:06. That's of course assuming that everyone has synced their time. I'm sure everyone here runs an infrastructure where it's all locked to NTP, and all of my logs are getting kicked at exactly the same time. I don't have time zone mismatches that then I sometimes remember and sometimes forget to correct for. Everyone here logs to Zulu time, right? Everyone puts all the logs in Zulu time? Yes? Yes? If not, go do it. So, anyway. Of moderate to, well, not even moderate. This is pretty useless in a containerized environment. Way too many endpoints and way too ephemeral. There's nothing here that actually tells me what this thing was. If I start writing policies, there's some things I can do. So I can start generating logs that show me what the actual thing was. What was its actual identifier in the orchestrator? What namespace it was in, even what policy it went through. So I can see in that log that a given flow was allowed or denied based on a specific policy. So I know that matched the foo client to foo producer policy, or it matched and was denied the PCI things can't talk to non-PCI things policy. So I can now not only see the flow, but I know why it was allowed or why it was denied. And what were the other characteristics? We can even show labels in a Kubernetes environment in these logs. This thing had these labels at that point in time. So you now have an ability to have a set of logs that's durable and useful over a long period of time, and they've actually been pre-classified as to what kind of traffic this is, or at least what kind of traffic the policy system thought it was, i.e. it matched a given policy. So if all of a sudden you see a policy being used that you expected only to be used certain times of the day, and now you're seeing it used all the time, maybe that's an indicator that you might have a problem. That might be something that, for example, a machine learning system could pick up on by saying, gee, this policy was usually only used at these points in time, and now it's being used at other points in time. And this is a little more of a breakdown on the policies that you can kick out if you're policy-based, or the logs you can kick out if you're policy-based. And we also have the iTest chart, so you can actually visualize what's talking to what. All right, any questions, folks? Yes?
You install the software on the Kubernetes master and all the worker nodes, or how exactly you do it?
So the way our project works, so this is the concept, but this was obviously, I demoed my product. So our open source and commercial product doesn't really install too much on the master. There's some installs on the master, but mostly it's on every worker node and every master node as a Kubernetes node. And then we launch some number of controllers, etc., that exist in the Kubernetes cluster. But there's not really much that lands specifically on the master as needing to be on the master. It just we need controllers to talk to the Kube API server. We need key value store. We need to be able to store things in the Kube API server. We need an agent that sits on every host, which controls the networking and the policy enforcement. But everything else you saw here is just the graphics and all that's just an application, the server running in your kube cluster. Yes?
So at 100,000 containers, that Death Star picture never works.
So the reason I'm having run 100,000 or a million endpoints. So the view on this is one visualization. There are others. But the idea is you would probably then scope the view down. I only want to look at the demo one namespace or a specific application, so you can start scoping it down to.
True, but there might be 10,000 of those.
Exactly. So at some point,
what search capabilities do you have on string substrate?
So I'm just going to do that. So we have, we assume for most production users, they will already have a logging analysis system like Splunk or Elk Stack or an EFK stack. If they don't have anything like that, then we do have